Take a look at this configuration of raw mathematical symbols and tensor arrays orbiting right in front of us. Every lesson so far has been leading to this exact point. We've learned how tensors hold data, how AutoGrad calculates improvement, and we even wrote our own weights and gradients by hand. Strip away the jargon. A manual neural network is an assembly line. Raw data blocks pass through transformation nodes, outputting a refined prediction. But adding nodes creates friction. Writing every calculation by hand, creating weight tensors, multiplying matrices, and zeroing gradients is repetitive and error-prone. This approach hits a hard ceiling at scale. Real-world AI models often require 50 layers or 1,000,000 parameters. Hand-writing thousands of isolated tensors and keeping their shapes aligned is a recipe for silent, breaking bugs. PyTorch solves this with nn.Module. Notice how that tangled web dissolves and reforms into these sleek, interlocking blocks. This is a building block system designed to replace fragile manual steps with encapsulated, production-ready architecture. Graduating to industrial-scale AI requires moving past hand-rolled code. We use these pre-engineered components to handle the mechanical heavy lifting. Every custom PyTorch model follows a specific structural skeleton. When you inherit from class model nn.Module, your code gains access to all of PyTorch's internal machinery for tracking and optimization. We define the model components inside a init. This is the blueprint stage. We declare the layers, the individual machines, before data moves. Then, forward acts as the conveyor belt. It draws a path connecting the blueprint, deciding the order data passes through those layers. The nn.Linear layer is the workhorse of this system. It replaces manual math by automatically generating weight matrices and bias vectors sized correctly for your specific input and output counts. Inside this block, PyTorch handles the overhead for us. These internal weights and biases are automatically registered for AutoGrad tracking, which is why you no longer see requires grad true in the code. Utilizing these pre-built blocks allows you to focus on the high-level architecture of your model, rather than debugging the raw matrix operations of every individual layer. However, stacking these linear layers alone isn't enough. Mathematically, adding multiple straight-line functions together only ever produces another straight line. No matter how many layers you add, the logic remains rigid. Real-world data patterns are rarely straight. Tasks like image recognition or language processing involve complex, curved relationships that a straight-line model cannot capture. To model those curves, we use activation functions like ReLU or Sigmoid. Think of them as valves placed between layers. When data hits these valves, they introduce a nonlinear bend into the flow, allowing the network to reshape its internal logic. By placing these activations between layers, we create what are known as hidden layers. These are intermediate stages where the network builds its own internal, compressed representation of the data. This allows the model to extract complex structure before it makes a final prediction. To keep these sequences organized, nn.Sequential chains the layers and activation bends together in order. This keeps the code readable even as the network grows to dozens of layers. This combination of linear transformations and nonlinear bends is the mechanism that allows a neural network to model the complexity of the real world. To manage all these parameters, model.parameters acts like a funnel, instantly gathering every trainable weight and bias into one unified list. This entire list plugs directly into our update node, ensuring every parameter is updated simultaneously. We also gain access to built-in loss functions like nn.BCELoss. It handles the same error measuring math we did by hand, but with the numerical stability and safety checks required for production models. The final piece of the engine is the optimizer, like torch.optim.SGD. It handles the calculus of the gradient descent updates and manages the zeroing of gradients for every parameter automatically. Look at the side-by-side comparison. Our old manual method required multiple lines of subtraction logic for every parameter. With the optimizer, that process shrinks down to 2 clean commands, optimizer.step and optimizer.zeroGrad. These tools automate the mechanical execution of training, which allows the network to self-optimize efficiently at massive scale. The entire training loop can be summarized in 5 steps: the forward pass, the loss calculation, the backward pass, the parameter update, and the gradient reset. During the forward pass, input data travels through the sequence of linear layers and activation bends. The data is reshaped and compressed as it passes through each ring until it emerges as a single prediction. Once we have the loss, a backward pulse travels in reverse through that exact same path. It illuminates every ring simultaneously, updating the weights in each layer to improve the next prediction. Mastering both the manual math and the nn.Module abstraction ensures that your architectural decisions are grounded in the actual mechanics of how a network learns. You can find all the code, detailed notes, and the roadmap for building larger architectures like convolutional neural networks at github.com/rohit7696/PyTorch from scratch. Using nn.Module is a choice to leverage established engineering so you can focus on the higher-level design of the intelligent systems you build.